Nuclear fusion occurs when the nuclei of two or more small atoms, like hydrogen, combine to create one big nucleus. For example, hydrogen isotopes deuterium and tritium fuse to produce helium, a neutron, and energy. For nuclear fusion to occur, isotopes must be exposed to high temperature and pressure. At that temperature, the hydrogen is plasma, which is an extremely high energy state of matter. Scientists are looking for ways to use nuclear fusion energy for our own use. How does nuclear fusion work on Earth? The sun creates the right conditions for fusion, but on Earth they're much harder to achieve. Hydrogen isotopes must be heated to extreme temperatures, kept dense, and confined long enough to allow nuclei to fuse. Fusion research programs aim to achieve these conditions. Once achieved, there will be a positive net yield of energy, where more energy is produced over the energy absorbed in the reaction. In fact, released energy from fusion reactions is about 4 times more than nuclear fission. For example, in a fusion reactor, deuterium and tritium are fused together to produce helium and a neutron. The neutron would blast into the lithium blanket around the plasma and undergo a nuclear reaction to produce more tritium. The tritium would be fed back into the nuclear reactor. There are many other ways where fusion can be achieved for energy. What area of study is nuclear fusion, and what other fields are related to it? Nuclear fusion falls under energy changes, rates of reactions, and the nature of energy and heat pertaining to nuclear energy. This genre of study combines elements from applied physics, plasma physics, mechanical engineering for reactor designs, material science for reactants, and electrical engineering when it comes to converting nuclear energy to electrical energy. Who is involved in nuclear fusion and how are they contributing? Today, many countries take part in nuclear fusion reaction and programs. For example, the European Union, USA, Russia, Japan, China, Brazil, Canada, and Korea are a few. Nuclear research costs a lot, thus international cooperation is needed. The following are different reactor designs. Tokamaks are devices with donut-shaped magnetic chambers that confines plasma. Examples of these devices include Joint European Torus, or JET, Mega M Spherical Tokamak MAST from UK, the ITER, or International Thermonuclear Experimental Reactor Project in France, will be the largest tokamak when it operates in 2020. K-STAR, Korean Superconducting Tokamak Reactor at the National Fusion Research Institute, or NFRI, will be upgraded to study longer laser pulses for improved performance and efficiency. The Chinese Fusion Engineering Test Reactor, CFETR, is to be larger than ITER and is due for completion in 2030. Stellarators are devices that contains plasma within magnetic fields in a more complex design. Examples of these include large helical device at Japan's National Institute of Fusion Research, which aims for the best magnetic configuration for plasma confinement. Another is TGII operation in Spain. Another one is Heliac-1 Stellarator, Australian Plasma Fusion Research Facility, which is capable of wide-range plasma configurations and improved magnetic design. NIF Laser System, inertial confinement fusion, was the first to have more energy produced than absorbed in a fusion reaction. K-Demo, which is a result of cooperation from the U.S. Department Plasma Physics Laboratory and South Korea's National Fusion Research Institute, would be the first plant to actually convert power to an electrical grid. It is expected to produce electricity in the future. Osaka University Institute of Laser Engineering in Japan suggests that ignition can be achieved at lower temperatures with a second very intense laser into a compressed fuel. How are we using nuclear fusion in society? Research and experiments continue to develop a fusion reactor where we can get more energy than we input. Fusion will help solve our growing energy consumptions and its effect on the environment, resources, economy, and etc. It can provide a large source of non-polluting energy which is clean and inexpensive, and positively affect potential employment in energy sectors in the future, including those who are developing and designing reactors now. How are we using nuclear fusion in terms of our environment? Fuel ingredients for fusion are harvested from the environment. Deuterium is naturally and very abundant in seawater. However, tritium occurs naturally in small quantities. It can be made by a nuclear reactor or within a fusion system from lithium. Lithium is found in large quantities in the Earth's crust. Scientists are studying ways to use byproducts of fusion via this fusion torch concept. This involves the cooling of fusion plasma to produce steam which is used to incinerate garbage and solid wastes. The small molecules created are collected and used as raw materials for other industries. Although fusion offers a large source of energy for many generations, it also has many scientific, environmental, and engineering challenges. What is good about nuclear fusion? Fusion would not contribute to acid rain or the greenhouse effect, for there are no carbon emissions. It's a new, cleaner way to supply our increasing energy demand as concerns grow over climate change and declining supplies of fossil fuels. It can also dramatically lower our carbon footprint. The fuels, deuterium and tritium, are abundant in the environment. Also, it has a high energy efficiency, where 1 kilogram of fusion fuel can give us the same energy as 10 million kilograms of fossil fuels. Finally, there are no chain reactions, therefore easier to control or stop than fission reactions. So what is bad about nuclear fusion? Fusion is not expected to be commercially available until 2050. It also has radioactive waste problems due to its structural materials becoming radioactive. There is also possibility of release of tritium into the environment. It is radioactive and very difficult to contain, so it can easily pollute water and other systems. Tritium can also remain a threat for health for about 125 years after its production, which is very dangerous. How are we trying to improve nuclear fusion? There is still difficulty to designing a reactor that can sustain extreme heat within a period of time while safely containing the plasma without leakage or creating a negative net energy. Currently, most reactions include deuterium and tritium reactions, but we hope for a deuterium-deuterium reaction, but this requires higher temperatures. There are two main approaches studied, magnetic confinement and inertial confinement. Magnetic confinement involves the use of strong magnetic fields to contain hot plasma in a donut-shaped magnetic configuration. Deuterium-tritium plasma are confined by magnetic field under pressure and heated to fusion temperatures. Magnetic fields are ideal for confining plasma because it prevents particles from coming into contact with reactor walls. Inertial confinement involves a laser or ion particle beam to be focused precisely on a small pellet of deuterium-tritium fuel. The laser heats up the outer layer of the material and compresses it, resulting in fusion conditions. The energy released would heat the surrounding fuel, which undergoes fusion, leading to a chain reaction known as ignition, as the reaction spreads outward throughout the fuel. Research is also being done carried on several types of sterilators. Sterilators have higher plasma stability compared to tokamaks, thus have more potential for steadier and continuous operations. But they are much complex to design and thus harder to build than tokamaks. If fusion reaction can be slowly released and controlled, it can produce electricity. 3 things are preventing this from happening. Temperature. To heat samples to this high temperature, we need magnetic fields or lasers. Neither one has been yet to be achieved efficiently to get the desired temperature or net energy. Time. The charged particles or nuclear plasma must be held together closely and long enough for fusion to start. Containment. Since the plasma has a charge, magnetic fields can be used to contain it, but if it leaks, the reaction won't take place. Scientists are yet to create an efficient magnetic field that won't allow plasma to leak. Thank you.